A good day to all of you. Today we will see how far we can progress on transformers. So, this is all about transformer. What is the transformer already done? Input, already. So, you have at least 2 coils, right? And you have a magnetic circuit in that. Those things you already know. By the way, transformer may have more than 2 coils. In that case, we normally say one which is connected to the source is primary, which is connected to the load can be secondary, the another can be tertiary. All those things will come one by one. For the time being, we have 2 windings. And when we last time discussed that, you can think of a core, and it is almost never these coils are put one this side and the another this side. It's almost never done that. How it is normally done? You have part of low voltage coil first, and then remaining part of the low voltage coil here, and then on top of that you can have say high voltage coil this side, and then high voltage coil this side, high voltage coil this side. So, you can see that these are high voltage coils, these are high voltage coils. You can think that half of the high voltage coils on one limb, half on the other. Why it is done like that? To make leakage minimum. This is a typical core type construction. You may ask why high voltage coils are put in outer layer and low voltage coil. This is low voltage coil inner layer, this is low voltage coil, this is low voltage coil, and this is low voltage coil in the inner layer, because the transformer core is grounded. So, the low voltage needs less insulation, the high voltage coils need more insulation. So, if you put the high voltage coils at the outer layer, it is better to provide insulation. So, those are construction details of the transformer, those we will learn at the end. But for the time being, it is enough to know that you have a coil, you have 2 coils, and then for all our purposes we will have this representation, one coil this side and the other coil the other side. We already know, high voltage, suppose this is my high voltage and this is my low voltage, they are distinct. Whichever will be connected to the source will be primary, whichever will be connected to the load will be secondary. By default, we will consider, will put nomenclature like V1, I1. So, this 1 all indicate primary by default, and this side V2 and this side I2 by default they are secondary. That is all. Let us go ahead. So, next slide. Okay. So, I have to actually erase this one also. Yes, we already discussed about transformer rating the last time. Typical transformer rating, you have voltage rating, high voltage rating, low voltage side voltage rating, volt ampere rating, single phase or 3 phase, 50 hertz like that. One aspect about the rating I would like to mention here, when you talk about this 2 voltage ratings, say V1, V2, in this particular case it is 11 kV and 440 volts. When we talk about this voltage rating, so you can think that these are the 2 coils. When V1 is applied, when V1 applied here, this is V1 applied here, when the transformer is at no load, V1 is approximately is equal to E1 this side, approximately is equal to E1, and then E1 E2 is A is to 1. That way related E1 by E2 is A. So, here if you do not connect a load, if you put a voltmeter, right, if you put a voltmeter here, you actually measure the E2, right. But when you put a load, depending on the load, right, depending on the load current, this voltage will be different. We will come to that in regulation chapter. What I would like to emphasize here is, when at no load, this E2 is unique, and we consider this V1 is 11 kV. This E2 at no load is actually V2. So, V1, V2 is unique. For all calculations, in many books we will see that V1 and V2 they are rated voltage. When you consider rated voltage, rated conditions, right. But when you talk about V1, it's 11 kV rated, we understand. V2, 440 volt. If you say V2 is rated, it all depends on the load, power factor, depending on the load, depending on the power factor, the terminal voltage. If you talk this terminal voltage to be V2, it will actually change. But when you say 11 kV and 440 volt, what is this 440 volt? When you talk about rating, this 440 volt is actually the voltage that you get at no load. So, V1 V2 concept is clear, right. And when we calculate both the side current, we simply divide by KVA divided by voltage, KVA divided by voltage, you get the current, right, and those currents we take as rated load current. Okay. Going ahead with this, okay, first let us rub it out, and then we go ahead quickly. We will see how far we can cover the syllabus today, and then okay. The back, I have to put the back here. Ideal transformer. Ideal transformer part already we learned yesterday. Ideal transformer, no loss, no leakage, linear magnetic circuit require negligibly small magnetizing current. So, ideal transformer, if you would like to model, then this is simple. This is this here, this is this here, and this is this here. This is a ideal transformer. Okay. So, you put your V1 here, you put your V1 here, and as per our convention, we put this is minus of V1, this side we put E2, and this side we put V2. E2 is equal to V2. You do not need any magnetizing current at no load. Small, it is a negligibly small magnetizing current. You can see very small magnetizing current to produce the flux. Okay. And then when we try to load this, let us see what happens. So, okay, voltage current relations. Let us still ignore winding resistance and leakage and consider magnetic circuit is linear. Okay. If we do that, then how was the phasor diagram? Because it is better to check the condition rather than drawing all those waveforms, voltage current waveforms. If I draw the phasor diagram, it is very quick and very easy to understand. Magnetic circuit linear, ignoring leakage. So, if we consider flux to be our reference phasor, we all know small amount of current, negligible amount of current to produce this flux. I phi will be there. You have here, suppose it is step down transformer. So, you can consider, so then E1 will be more. So, suppose this is E1, this is E2, from here to here, this is E2, and then on the other side you can go to minus of E1, and that will be your V1. Simple phasor diagram. Okay. And then next, if we consider the magnetic circuit is okay, I will go to the previous one, is not linear. Magnetic circuit is not linear. Then last time we have seen that what will happen? You have a third harmonics coming into picture, and we neglected third harmonics. Because see, in this phasor diagram, the phasor diagram remains the same. In this phasor diagram, all quantities are of fundamental frequency, which is 50 Hz here normally. So, you cannot actually show another component which is rotating 3 times the 50 Hz. That is not possible. So, we do not show the third harmonics component here. Third harmonics is actually very negligible. Next year, in second year electrical engineering students, when you come to electrical machines class, you will learn in detail what this third harmonics fellow actually does to transformer operations. Very interesting behavior of this third harmonics. For the time being, we neglect third harmonics and carry on. Good. Fine. Next, if we go to next topic. So, not linear and having hysteresis, okay? And we have checked that last time. When you consider hysteresis, we have a new component coming in. We have a new component coming in. May I have different colors? Anyway, so and that component will be in this part, hysteresis component, right? So we can say this is hysteresis component in phase with V1. So V1 and IH will be the hysteresis loss. The remaining part is actually same, and we also discussed the other day in transformer core you have eddy current loss. To take care of hysteresis and eddy current loss, you will have another component here, because loss can only be accommodated with an in phase component, right, in phase with a voltage, applied voltage. So, you can clearly see that this can be your eddy loss component IH and IE, and then this we can sometimes we say this is as IH plus C, hysteresis and eddy current component, and sometimes this is just a coal loss component IC, they are all same, and this is this, and they are actually in that direction. Okay. So, if we carry forward, then we have transformer no load, equivalent circuit and phasor diagram. So, phasor diagram is this. If we try to develop the equivalent circuit, this is of course easy, right. So, the equivalent circuit, how you think of the equivalent circuit? Still we are neglecting resistance and leakage. If we neglect that, then this will be something like this. So, you have R resistance to take care of this component, which is coal loss component, say IC. So, IC will be flowing through this, and you need another inductance, say we put J, sometimes X phi, sometimes Xm, right, they are same, right, this side. So, this is as well as sometimes I will use X phi, sometimes I will use Xm. So, J X phi, that is it, and then through this you will have I phi, flux producing current I phi, and sometimes I will write Im, magnetizing current I phi or Im. If you put this, the transformer modeling part is done, and then what you can do, you can just show the ideal transformer, just extend that, and you can show the ideal transformer somewhere here. Okay, then I will erase this part, and then put the ideal transformer here. So, you can just put 2 winding. Perfect. So, transformer at no load, you can see the secondary, there is no load on the, and this is ideal transformer, there is no current flowing over here, no drop, this is just A is to 1. So, no load we can take care. If we now go ahead fresh, then let me rub it out all, and then let me see ideal transformer loaded phasor diagram is already done, transformer phasor diagram. Okay. Now, the real transformer part we are actually discussing. Okay. Equivalent circuit refer to primary, that will come later, transformer phasor diagram. Now, for the real transformer. So, what is there? For the transformer now, you can clearly think, if these are the 2 windings of a transformer, then obviously this is a mutual, there will be some leakage over there, some leakage will come into picture. This winding has some resistance will come into picture here, some resistance come into picture here. So, and the loss will come into picture. So, therefore, if you see the transformer phasor diagram, transformer equivalent circuit for the real transformer, so you can see that this is for the primary, this is for the primary, and this is for the secondary, this is for the secondary side. Okay. For the timing, I am not putting the coal loss branch, right. You can think that to take care of, if I put it like that here, then you have to consider some component here, some component here, and something like this here. You have to put this is there and this is there, Okay. So, if I do not put that for the time being, okay, then this is the equivalent circuit of a transformer. And for this transformer, if we connect a load, and then if we say this is V1, this current is I1, this is, as per our nomenclature, this is minus of E1, this is E2, and this is V2, load voltage is V2, this is R1, this is JX1, this is R2, this is JX2, and this is I2, All these things you can easily identify. Now, this is for a real transformer. We have for the timing ignored the core loss component and the magnetizing component. Normally in transformer, to show the iron core, we put two parallel lines. How to draw the phasor diagram for this transformer? How to go ahead? So, we start from V2, right. So, we start from V2 here. So, this is my V2, and then current I2, depending on this V2 and I2, depending on the load power factor, you can draw the I2. So, this is my I2, right, and then I2 and R2 drop. So, add it up, I2 R2 drop, this is I2 and R2 drop, you can add it up, J times I2 and X2. So, these two drops added, and then added to V2, you have this side E2. So, from V2 you came to E2, right. Once you have E2, considering this is step down transformer, so E1 will be more, and E1 E2 are in same phase. So, put the E1 here. So, you have E1 this side. Okay. And where is the flux located? Ahead of E1 E2 by 90 degree. So, flux is somewhere here. This one and this one is 90 degree, flux in this direction. Okay. And then you have to look at minus of E1. So, on the other side you can easily go to look at minus of E1, right. And then when I2 current will be flowing, what will be I1? When I2 current will be flowing, what will be I1? Okay. So, to explain that, what I will do, I will take 1 minute to first discuss what happens when a transformer is loaded. So, suppose this is the transformer, and you can think that this is the one winding side, and this is suppose the other winding side. For the timing, again think that the transformer is ideal, it will help. So, and this side we put a V1, right, and then some current will be coming to produce a flux. If you can check, this is the current direction, then the corresponding flux, just trying to get a different color, no, yes. So, the flux you can locate something like this, So, flux, you apply thumb rule, you can clearly see the flux will be something this way, that way. Okay. Right. How can you calculate the flux? So, this side you already know that V1 is finally N1 d phi by dt. V1 is minus of V1 and V1 is N1 d phi by dt. So, flux will be decided by these equations from the primary side. And when, of course, this flux is linking, this is N1 and this is N2, flux is linking the secondary, and when we connect a load across the secondary, because you have E2 here, some voltage E2, okay. So, current will flow. Which direction the current will be flowing? The current, whenever current will be flowing through N2, this will produce an MMF, and that MMF must oppose the initial MMF. this MMF, when current will be flowing through number of turns, N2 number of turns, some MMF will be produced, some flux will be produced. This flux must oppose the original flux. That was for Lentz's law. That cannot, go in the same direction. The flux and then further flux will increase. That cannot, that's not a stable situation. So that must oppose. So if it has to oppose, we can clearly see which direction the current will flow this side. If it has to oppose, this should be from this side, this direction. This should be this direction. This should be this direction. So this will be this, and this will be this clearly. And apply thumb rule again here, and then if you can see the MMF will actually oppose the MMF produced by the N1 number of turns. Okay, and then so we can now imagine that my E2 is there, and my I2 is flowing like this. The moment I2 is there, into I2 MMF will be produced, and this MMF will oppose the initial MMF, right. So the flux will try to decrease. The moment flux will try to decrease, what will happen? The moment will try to decrease, it cannot decrease because V1 is N1 d phi by dt. So decrease in flux will be arrested through increase in current from this side, How far the current will increase? Such that N1 I1 should be equal to N2 I2, right. N1 I1 should be equal to N2 I2, because for magnetizing we are not considering any amount of current, negligible amount of current, and those we are neglecting. So N1 I1 should be equal to N2 I2. In fact, N1 I1 plus N2 I2 should be 0 in the magnetic circuit. So N1 I1 should be minus of N2 I2. From here you can calculate I1 is minus N2 by N1 into I2, and should be in the opposite direction, right. So this is the principal operation of a transformer. Whenever you load in the secondary side and MMF will be produced, that MMF must oppose the primary MMF, right. The flux will be opposing the primary flux produced by the primary, right, and then the flux will try to decrease, but flux will not be allowed to decrease by this equation. So the current intake will be more to cancel the MMF produced by the secondary side or the load side. So this must be true. What we neglected is the current, a small amount of current is there, should be there from the primary side to maintain the flux in the core. Okay. Now we will go back. So we know that I1 will be there, which is in the opposite direction of I2, and then in the ratio N2 by N1. So if we go back to here, okay. So if I2 is this side, right, if I2 is this side here, I1 will be this side. So let us go I1, something like this. So this will be I1 opposite, okay, and then maintaining that ratio, so that N1 I1 is equal to N2 I2, and if I1 is this side here, I have to add R1. So you can add I1 R1, nothing to be scaled, right, and then J I1 X1, you can think J I1 X1 ahead of this one by 90 degree, and that will be V1, adding it up. So you can see that this will be your V1, this will be your V1. Phasor diagram of the transformer. And then if you now consider that the magnetizing branch is there, right, if you now consider the magnetizing branch is there, what will happen? So you have one more component. So you will have one more component. You can consider this to be, this side to be I phi, flux producing current, small component this side to be core loss component IH plus E. You can add this up, which is actually I0, no load component, the I1. Now what do we call this? Is a no load component. We consider the magnetizing branch over here. So this current is always there flowing through the primary side, and when the load will come I2, then the load component I1, so we say this is I1 prime, right. So how I1 prime is decided? You already know. So N1 and I1 dash prime and N2 and I2 must be 0. So originally in the transformer I0 current was flowing, of that IC is a core loss component, I phi is a magnetizing component, that was always there, that was there to produce a flux, but when the transformer was loaded, immediately there is a component coming in which is I 1 dash to cancel the load MMF such that the flux is remaining same, which is actually produced by I phi. So, what then will be the current in the primary side? I 0 plus I 1 dash. So, the vector addition of that, then you have this is I 1, right. So, I 1 is actually, so you can write this side I 1 is basically I 1 dash plus I 0 all vector, just a vector addition, and the remaining phasor diagram is just perfect. Okay. This is, and you can think we have considered the load power factor to be say theta 2, which is lagging. You can consider leading power factor, you can draw the phasor diagram, you can consider unity power factor, you can draw the phasor diagram. So, you can continue. Let us go ahead. So, next is, before that let me draw this out. Let me just run this out, and then let us go ahead. What will be doing next? Okay, equivalent circuit referred to secondary. Okay. Now, we have the equivalent circuit. This is very important. We have now, see the equivalent circuit. I think first we should go to equivalent circuit referred to, we have to go to here. Approximate equivalent circuit, but we will go to previous one, refer to primary side. First, let us do this, and then we will go to other thing. So, now consider that, okay, sorry, primary, and then it is here. Okay. Now, consider that you have this transformer. Quickly, you consider that you have this transformer. We have this transformer, and then load is applied. So, this side we have V 1, this side of course I 1, this is R 1 as usual, this is J x 1, this side we have as per our convention minus of V 1, this side we have minus, this is E 2, this is R 2, this is J x 2, this is V 2, and this is I 2. Okay. And this is A is to 1, this is A is to 1, where A is N 1 by N 2, A is E 1 by E 2, we all know that, A is something like that. So, A is to 1. Next, you can see if we try to have some exercise, this part, if we try to have some exercise, we will try to consider a fictitious secondary, something like this, and then just check what we are doing. We have a fictitious secondary where the number of turns of the secondary is same as the number of turns of the primary. So, now this is n 2 times, so we make it A into n 2 times now for this one. If it is that, then this is of course E 1. A times E 2 is E 1, A times N 2 is N 1. So, we are thinking of a fictitious secondary having the same number of turns as of the primary. Then what happens? If this is E 1, the current that was flowing, what we want, the effect of this fictitious secondary should be magnetically and electrically same as the original one. So, if it is N 2 the number of turns is A times N 2, the current that must be flowing must be I 2 by A. Why? Then only A times N 2 into I 2 by A will produce N 2 I 2, same MMF. So, if we have a secondary with N 1 number of turns and the corresponding current I 2 by A, magnetically it is same. The transformer will not be able to understand, identify fictitious and the original, they will behave exactly in the same way, produce the same MMF. Now, how about the electrical equation? The electrical equation was E 2 is V2 plus this is I2 and R2 plus Jx2. This was the original equation. If I multiply by A, then this will be AE2, this will be AV2 plus this is AI2 and this is R2 plus Jx2. Same equation, Kirchhoff's voltage law, same Kirchhoff's voltage law, only A times. AE2 is E1, so now this is E1, it looks like this is E1 now. This is AV2, so this is AV2. Current must be I2 by A. So, if I make it I2 by A instead of AI2, to keep this equation same, I must write inside A square R2 plus J A square X2. Then the equation is same again, right. So, what is happening? This is E1, this V2 become AV2, AV2 sometimes we put it V2 dash, AV2 is V2 dash. So, now this is V2 dash, I2 by A is I2 dash, right. So, and then this R2 and this become R2 dash and this become X2 dash. So, the winding resistance and leakage also get changed. So, now you check, instead of this original secondary, if we consider the new secondary, they are actually same in all respect, right. The only thing while doing this, we made the E2 is now AE2, we sometimes say E2 dash, not, we should not put E2 dash here, okay. E2, if we should put E2 dash here. So, E1 is basically, this E1 is basically, we can say E2 dash. Normally, we put dash when we refer to the primary. Why we say this is referred to the primary? Because the voltage in the secondary side is now E1 of the primary side voltage. Okay. So, now if we consider this primary and this secondary, right, this primary and this secondary, and then try to draw the phasor diagram again, what happens? So, let us go again and then let us just go to the next one. Next one, okay. So, then what is happening? So, we have, if we start from AV2 which is V2 dash, now which is V2 dash, we have I2 by A which is I2 dash, theta 2 of course remains same, and then we had this side I2 dash and R2 dash, we have this side J I2 dash and X2 dash, and we have this side E2 dash which is actually E1, right. And then on the other side we go where this will be minus of E1, remaining part what we normally do, we can still do that, we can locate your phi, or you can locate your, if we consider also no load component, we can locate your I0 here, we can locate your I1 here, right. By the way, I1 and I1 dash here, I1 dash and I2 dash, I1 dash is how much this time? Will it be I1 dash? But note, this is a load component, this is not the referred quantity, right, that has to be understood. Normally dash we put for the load component, but this is actually the load component of I2 dash, and then if we put it here, this will be your I1, that will be your I1, and then we put I1 R1, we put JI1 X1, and then we can make your V1, this V1. Because your E2, E1 and E2 dash same, if we go back to here, if we now connect, if we do not care about this, if you do not care about this sign, because magnitude wise E1 and E2 dash is now same, E1 and this is also E1. If we now connect this one with this one and this one with this one, right, then what happens? So, we go again, we go to the next page. So, what we are trying to do? We are now trying to do, this is x1, so this is there, this is there, and then this is there, and then this is, and then you have a load here this side. This is the situation. So here you have a, this is V1, this side now we say this is V2 dash, this side R2 dash, this side X2 dash, right? And then suppose this one and this one, this is E2 dash is equal to E1 this side, this is E1, right? If we do that, because the voltage wise they are same, and this is ideal transformer. So now this I2 dash and this I1, if we neglect the magnetic branch, they are actually same, because I2 dash is, you know, I2 dash is I1, I2 is I1 by A, and corresponding to this, if we draw the phasor diagram, then we have here V2 dash, we have here, this is I2 dash, okay, and then we add it up. So this is R2 dash and I2 dash, we all the way add that, this will be your E1 and E2, okay, and then I2 dash is equal to I1. So if we add it up, next from this side you can add I1 R1, this side you can add Ji1 X1, and this will be this side, this is V1. And for transformer this is enough, this is simply enough, because normally we need for a transformer the voltage current on the secondary and voltage current on the primary. Never we need the phase of, say, secondary with respect to the phase of the primary phase voltage, right. So because of that, this will actually simplify if you need not really consider, this one E2 and then minus of n and do the phasor diagram. So you can further simplify. This is because just a series equivalent circuit. So you can consider one resistance here, one reactance here, and then the load, one and then the load. This is very, very convenient over here. This is V1 now. So this is your, this is V2 dash, and this will be now RE1. This will be now XE1. This will be your I1 or I2 dash. What is RE1? It is easy to, RE1 is the effective resistance referred to the primary side. So R1 plus R2 dash. What is XE1? X1 plus X2 dash, something like that. Okay. So what is the advantage of here? The advantage is the whole of primary and secondary, you can club it into one resistance and one reactance, and then you can make a very simple equivalent circuit. Probably you are thinking where will go the shunt branch, because shunt branch was somewhere here, right. For the shunt branch, you can consider the shunt branch somewhere here. So to do that, we will go to this stuff again. Okay. So I think I do not need this. So the shunt branch part, we can consider equivalent circuit for the primary. So this is to the secondary part will come later. Approximate equivalent circuit. So in the approximate equivalent circuit, we can normally what we do. So we have, suppose, that resistance, that reactance, secondary side, and we have here, and then here we put this one and this one. That's it, right. So this is RE1, this is XE1, this side is V2 dash, then this side must be V1, and this is your RC, and this is your X5, right. So this is approximate equivalent circuit of the transformer. Quite often you will see, depending on the situation, we will sometimes consider the shunt branch, sometimes we will not consider the shunt branch, and we will explain what we are doing and why we are doing. But before that, the previous part, the previous part, okay, the refer to the secondary side, the primary part is done. The refer to the secondary side is your homework. You can clearly do that. It will be again similar. The only thing that will change here, because it is referred to the secondary. So, you can clearly this dash part will be only different. So, if here again, so this will be now V 2 and this will be V 1 dash, okay, and this will be R E 2, this will be R E 2 and this will be X E 2, okay, and you can consider this one also dash and this one also dash. And then what will be the current here? Not I 2 dash, but I 2. Okay. So, this is referred to the secondary side. You can do this as your homework. You can clearly check. Same principle as we have done. Having a fictitious, secondary. In this case, fictitious primary with n2 number of terms, and you can do that. Next is. Okay, next let us solve a problem quickly, because now this how to refer to the primary site and how to refer to the secondary site. If we solve these problems, it will be quite convenient and quite easy to follow. So, take this problem of 33 kVA 2200 stroke 220 volt single phase 50 Hz transformer has the following parameters. High voltage side, you can clearly see 2.4, so 2.4 ohm, 6 ohm. Low voltage side, the resistance is far less, reactance is far less. Find R 1 dash. When you put dash, that means you are referring to the other side. R 1 dash is R 1 referred to the 2 side. So, low voltage side, here you can clearly see that 1 refers to high voltage side, 2 refers to low voltage side. So, R 1 dash is R 1 referred to the low voltage side. Similarly, X 1 dash, R 2 dash is R 2 referred to the high voltage side. So, dash is the other side referred. So, you can calculate and then find effective resistance referred to the high voltage side, effective reactance referred to the high voltage side, effective resistance referred to the low voltage side, effective reactance referred to the low voltage side. Find total ohmic loss at rated load. Rated load you can calculate volt ampere divided by 220. So, 33,000 divided by 220 will be the load current in the secondary, 33,000 divided by 2200 will be the load current in the primary side. That will be the current. Ohmic loss is loss in the resistance, I square R loss. So, you can calculate. Interestingly, you can calculate separately. Okay. You can calculate separately the current in both the sides, and then that current square into the corresponding side resistance, and you can add it up, or you can just calculate the current in say one side, say low voltage side, and that current square multiplied by say low voltage side referred effective resistance will give the total ohmic loss. What I mean, so you have actually the circuit. If I say try to find say RE2, suppose this is my RE2, this is my XE2, and then rated current flowing, total ohmic loss at rated load. So, rated, if this is RE2, this is XE2, some rated load probably will be considered, and this I2 is the rated current. So, what is the total loss? I2 square and RE2, you can calculate. Effect, and similarly you can consider the total equivalent circuit referred to the primary side, then it will be I1, and then this will be RE1 and XE1, and I1 square RE1 also will give you the same loss. And then what was the second problem? The next problem, find the voltage to be fed to the high voltage side to have a circuit current of 150 ampere in the low voltage winding. Find power input. Okay. So, how do you do that? So, this part I think it is easy. So, if we go to the second, so you can clearly see that the turns ratio A is 10, sorry, no. So, here, so you can clearly check that turns ratio is 10 here, R1 dash is 2.4 by 10 square. So, this will be this, So, R1 dash is R1 referred to the low voltage side. So, now it is very less, X1 dash is X1 referred to the low voltage side, this is less. Similarly, R2 dash is referred to the high voltage side. So, R2 is originally less, when it is referred to the high voltage, this become more multiplied by A square, and similarly X2. Effective resistance you can calculate like this, RE1 is R1 plus R2 dash, XE1 is X1 plus X2 dash, you can calculate like that, and similarly RE2, this is XE2, this will be small letter. And then ohmic loss you can calculate 15 ampere rated current through the primary high voltage side, and this is to the secondary low voltage side, current is more. Ohmic loss you can calculate this way, I1 square into RE1, and that will be equal to I2 square into RE2, and that will be this, you can check. Now, for the next problem, what it was asked, it was told that this is a short. If it is shorted, to have a rated current flowing through this, what voltage you need to calculate, right? That was the questions, that was the problem asked. So, how can you do that? You can short it up, and then you can consider to the low voltage side, you can consider in the way it is done here, you can consider also the high voltage side. If you do it for the high voltage side, RE2, so you can consider RE1 and JXE1 also in this circuit. If it is RE1 and JXE1, then what current will be flowing? I1 will be flowing. So, then the voltage that you need is simply JD1. So, JD1 is just RE1 square plus XE1 square. You just calculate the impedance, and the voltage required is the V, in that case V, if it is in terms of 1. So, for that, not to confuse, this has to be this we can delete, and we can consider that this is RE1 and this is XE1, right, and then this will be I1, this will be I1. So, you can say this will be I1, then I1 is actually if 150 ampere is the rated current, shorted, when 150 ampere will be flowing through the secondary, through the primary is 15 ampere, right, and then you can just multiply. So, the ZE1, so V1 is I1, this I1 into ZE1. So, you can check 15 into ZE1, and then that will be your 211.5, and the power input is whatever loss will be in RE1, the same loss 1215. Alternatively, you can do the problem referring to the secondary side, because this is all referred to the primary side, and you can directly get the V1. If you refer to the secondary side, you can get JD2, RE2 and XE2, and then I2 150 ampere will be flowing, and you can calculate that, and then to get, you actually get then V1 dash. So, A times V1 dash if you calculate, and then you get the same voltage over here, and the power loss will be now I2 square RE2, you can get the same power loss. So, what you have learned that you can actually use this equivalent circuit either refer to primary side or secondary side, and you can solve your problem. Okay. So, because the time is not there, so in the next class we have plans to open circuit test and no load test and other test, other test we will do, and then this is there no load test, and you have Sasaki test that will find the parameters, and then the other part where you have to calculate voltage regulations, efficiency, auto transformer, and all the efficiency. This is your transformer syllabus. I am sure probably another 1 or 2 classes will complete the syllabus part. Hope you are enjoying. If you have any feedback, write emails. Thank you.